Okay, so in today's lecture, we're going to start talking about how to check whether our model explains the response variable well. Okay, so that question naturally follows after we have talked about setting up the model, doing estimation, inference, hypothesis testing, and prediction. So today we're going to delve into ANOVA, which stands for Analysis of Variance. Okay, and so as I mentioned, the question to keep in mind as we're looking at building these aspects of our adventure into checking our model, let us consider this question. So how well does our model fit the regression model? How well does our regression model fit the data? And specifically, we want to ask how well do the predictors we've used fit our response variable. So I'll explicitly say that fit our response variable. Okay, so because that's ultimately the aim of multiple linear regression is so how well can we fit Y, the response? Okay, so to start the story, we will consider how do we measure variability in our response? So let's start with this point. So variability. So what do we mean by variability in the response? Well, the Y's are going to have some variance, so it's going to be associated with the variance, and to measure that, we define what we call the total sum of squares. So variability in response. So we can define this quantity. Okay, and it will make sense in just a moment. And in fact, I gave you a preview of this on your homework. Okay, I asked you to do some calculations involving what I call the SS total on your first assignment. Okay, so this is what we call the total sum of squares. Okay, and so this is defined in terms of the responses. Okay, so only involves the responses because sum of squares total is meant to measure the variability in the response, and this is the quantity, the summation. So it literally is a sum of squares. So what are we squaring? We're squaring the responses difference from each response to the sample mean of our responses squared. Okay, so it's a sum of the squared differences between each response and the mean response. Okay, and so, why is this a measure of variability in the response? Well, this expression, as I asked you to connect in your first assignment, is closely related to the sample variance of what? Okay, so as you saw as seen in first assignment, this quantity, the sum of squares quantity, is closely related to the sample variance. So the responses are y1 up to yn. Okay, and specifically, you should have shown that indeed the sample variance is, which is, okay, in terms of the sum of squares total, the numerator is exactly the sum of squares total and then divided by n minus 1. So that's the connection between the sum of squares total and the sample variance of the responses. Okay, so it's simply without sum of squares total without dividing by n minus 1. Once we divide by n minus 1, we get the sample variance of y. Okay, so that's why that's why this quantity is one way to measure the variability in the response. Okay, so the key of ANOVA is this is to decompose. So ANOVA decomposes this sum of squares total into two pieces. Okay, so it's over here, the sum of squares total. So the ANOVA decomposition is to write sum of squares total in terms of two other sums of squares. The first one is the sum of squares regression, and then the sum of squares residual. Okay, and so let's give some intuition and write out what these names are. So this, as I just said, this is the regression sum of squares. And this one we've seen before. In fact, I've used this this notation before. This part is the residual sum of squares. And so the intuition is as follows. So this decomposition, I asked you to show a form of that in the simple linear regression case in your first assignment. And today we're going to look at how this works in general, including the multiple linear regression case. Okay, so the interpretation for the regression sum of squares, as we'll see shortly. So I'll just give you the description now. This measures the variation in the response that's explained by the regression model. Okay, so this is the variation explained by the model. Okay, so that's the interpretation of the regression sum of squares. And so the residual sum of squares, as we have already seen, because we use the residual sum of squares to estimate sigma squared. And what is sigma squared? Well, sigma squared measures the variance that's left over after fitting the model. It's the variance around the regression line. Okay, so using similar terminology, I can call this the variation not explained by the regression model. Okay, so that's an overview of the interpretation. Now, how do we get there? Well, we use this fact. So you saw a preview of this in your first assignment. So now let's formalize this idea. So we're using the fact that, okay, so if you take this expression, so the difference between each observation and the mean of the observations. Okay, so we'll take yi minus y bar. So the reason this works is we use the fact that this difference can be expressed equivalently if I add and subtract the fitted value. Okay, so remember we call mu hat the fitted value. It's the value of y at the regression line. So if I subtract mu hat and then I add it back, it's mathematically equivalent. And so the ANOVA decomposition uses this fact. Okay, now before I start looking at the math, let's draw a picture so we can illustrate why this is an intuitive idea. Okay, so the reason we start with simple linear regression is because things are easier to visualize because we can use a scatter plot between x and y to illustrate all of these relationships. Okay, so I'll draw a picture for the simple linear regression case up here. Okay, so we're going to visualize, so this is the visual for a simple linear regression case. All right, so let's imagine we have some data. Okay, so let's say we have some points like this, and there's some downward trend. So x and y have say, some negative relationship. Let's draw these quantities so we can see what's going on. Okay, so let's first fit our regression line. So let's add a regression line to the plot. So this is roughly the simple linear regression line that would go through this data. Okay, and so let's label this. So this is our regression line. So this line, the equation of this line is beta 0 hat plus beta 1 hat x. Okay, so that's the line of best fit. Okay, and let's also add another line to the data. So let's plot y bar. Okay, so y bar is simply the average of the values for y. So let's somewhere like about in the middle here. So we'll draw this line. Okay, so this is the line, the horizontal line y bar. Okay, so let's look at one particular point now. So let's focus on this. Let's say this point. Okay, so let's look at this quantity. So yi minus y bar. So this is the point I'm interested in, and yi minus y bar is this difference from this point to the y bar horizontal line. Okay, so this whole distance, so the corresponding line here, where it meets this line. So this is yi minus y bar. So you see this point is quite far away from the sample mean y bar. And what we see is that the regression line explains part of this difference. Okay, so let's see how this decomposition looks on this graph. So the difference between yi and its fitted value. So recall the fitted value is right here on the regression line. So we have this difference from the yi to mu I hat. So this part is yi minus mu I hat. It's the difference from the point of the observed value of the response variable to its fitted value. Okay, and you see in this example, this is part way to y bar. And so what's this remaining difference? Okay, so from the line, from the regression line to the horizontal line y bar, then is, well, it's going from y bar to mu I hat, the fitted values. So this is mu I hat minus y bar. Okay, so those are the three quantities that we described here. So in terms of color, I labeled yi minus y bar, the point to y bar, and then we've labeled yi to the fitted value, that's this piece, and then we've also labeled from the fitted value to y bar, so that's this piece. Okay, so that picture illustrates these three quantities and starts to give us some intuition for why this decomposition, which we're going to look at, takes the variability in y and decomposes into two parts, from the point to the regression line and then from the regression line to the overall mean. Okay, and so how is this going to behave then when the line fits the data well? So let's make a note here. So when the regression fits data well, then this on the whole, then, if the regression fits data well, then that means the observations, so yi's, are going to be close to their fitted value. So yi is going to be much closer to the fitted values than the overall mean. So this piece is, so the better the fit, the bigger this first piece in this decomposition will be. Okay, so when the regression fits the data well, then yi, so the observations tend to be much closer to mu I hat, and so this part is going to be larger. Okay, and so in fact, one other observation here is, well, what is the equation of this horizontal line? Well, in the simple linear regression case, this is simply a line of slope 0. Okay, so if this is like estimation line where beta 1, okay, so our estimate of beta 1, so beta 1 hat, the slope is 0. Okay. Okay, so let's add that point here. So it's close. It's going to be close to the fitted value. So in contrast, note that this is like a regression line with beta 1 equals 0. And we already talked about the interpretation of beta 1. Okay, that it represents the expected change in the response for a unit change in x. So in other words, if beta 1 is 0, which is one of the first hypotheses that we tested, that means that x and y don't have a significant linear relationship, right? So that's the intuition. Okay, so you have the fitted regression line compared to regression line where there's no relationship, and so the sum of squares decomposes the difference between the observation and a regression line with 0 slope, and so it measures how much of the variability in y is explained by the regression line that we fit. Okay, so that's the intuition behind the ANOVA decomposition. Okay, and so this is easiest to illustrate in the simple linear regression case. So with that in mind, let's look at the mathematics of this decomposition. And so again, you saw a preview of this in your first homework, because I asked you to look at this decomposition mathematically for the simple linear regression case. So we're going to generalize it to multiple regression. Okay, so mathematically, so the sum of squares total, so yi minus y bar squared. Okay, so this was the decomposition I asked you to show for simple linear regression on your homework. So it decomposes into these two. So they're also called sum of squares because the expression is the sum of squared quantity, and they look like this. So you have mu I hat minus y bar squared. So that's one sum of squares, and then there's the other part, which is for the, so this part is for the regression, and then this part is for the residual. And on your first assignment, I asked you to show that the cross term is 0. Okay. So let me add the labels. Okay, so this is our sum of square total. This is our sum of square regression. And then this is our sum of squares residuals. Okay, so that's the expression I gave you on the first homework. And I asked you to show in the simple linear regression case that the cross term, and so this is true since the cross term, so we have 2 times, so it's 2 times that, so we just need to look at this cross term, so sum of mu I hat minus y bar yi minus mu I hat. So this part is 0, and you showed this shown in homework 1 for simple linear regression, and so let's complete the proof for the multiple linear regression case. Okay, and this is also true. So what we're saying is this is also true for multiple linear regression. Okay, so let's see why that is the case. So since, okay, so I take this expression, this is equal to okay, so copy the first term, mu I hat minus y bar. Okay, and then we have, and then this part is simply the residual. By definition, it's the difference between the observation and the fitted value. So this is the residual, EI. Okay, and so if we expand the terms, this is summation EI mu I hat. And then I can pull out a y bar, so y bar summation EI. Okay, and so we've actually seen these things in terms of our vector notation. So we can write this as the dot product between the residuals and the fitted values. So I'm going to write this as mu hat transpose times the vector of residuals. And then we have y bar, and then this I can write as the vector of 1s, dot product between the vector of 1s and the residuals. Okay, so now we can see what this value comes out to. So if we look back at our notes from a few lectures ago, we looked at the geometric interpretation, right, of our least squares estimating equations, and this is actually what we're going to use. Again here. So let's remind ourselves what that equation was. So let's break this up into two parts. So first, let's look at this one. Okay, so this is actually this term is just 0 because okay, so it's here. So recall this one is one of the least squares equations. So the vector of 1s times the residuals is 0 is one of the least squares equations. Okay, so that part is 0. Now what about this one? Okay, so let's explain that here. So let's remind ourselves, what is the fitted value vector, mu hat? Well, remember that the fitted values is x times the estimate of beta, the estimated beta vector for the parameters. That's by definition the fitted value. And so what can we say about this this vector fitted values? Well, remember when we looked at the geometry of the least squares estimates. What can we say about this? Well, it's the matrix X times this vector, and so this entire thing is inside the span of the matrix X. Okay, so this is in the span of X. Okay, so that's something we stated a few lectures ago. Okay, and then relative to why is this fact useful? So this vector is in the span, and what do we know about the residuals relative to the span? Well, again, we need to recall that in that geometric representation, we know that the vector of residuals is orthogonal to the span of X. Okay, and so with that fact in mind, and then realizing that this fitted value lies in the span of X, so we know that these two vectors are therefore orthogonal. So therefore, mu hat transpose times epsilon must be 0 due to their orthogonality. Okay, so mu hat vector is orthogonal to the residuals. Okay, so we have shown then that through these two pieces that both of these are 0. This guy is 0 because it's one of the least squares equation, and this one is because of the orthogonality argument when we looked at the geometry of these squares. Okay, so this whole expression is 0. Okay, so we have shown then that indeed the sum of squares total decomposes into sum of squares regression and sum of squares residual for all of the regression models that we have looked at. Okay, so this picture, remember this helps us see that decomposition in terms of simple linear regression. So again, here you have the residual, and then this is the part of the difference, the difference between y and y bar. So this is the part that's explained by the regression line, and then this remainder is the residual, which is not explained by the regression. Okay, so we usually summarize this information in terms of what we call the ANOVA table. So let me introduce that next. So this is the analysis of variance table, and we'll see different variants of this, but let's start with the basic form of it. So the first column is usually labeled as the source. So this basically just gives labels to each row, and so we have our three components here. So regression from the regression model, from the residuals, and then total. Okay, the next column is what we call the degrees of freedom. Okay, so degrees of freedom is the number of parameters associated with, in this case, the regression model, so the number of predictors, so that's P. And then for the residual, we already talked about its degrees of freedom. It's the denominator of our estimate for sigma squared. Okay, so what do we divide by when we estimate the residual variance? Well, it's n minus p minus 1. So that's our degrees of freedom here. And so the total, the reason we lay it out like this is because these add up. Okay, so the degrees of freedom for the total is n minus 1. Okay, so how do we remember it's n minus 1? Well, if you're looking at the sample variance of your responses, well, if you have n values for your response y, then the degrees of freedom is what we would divide by in the sample variance of y. So that's n minus 1. Okay, so that's the degrees of freedom, and then we also write down the sum of squares quantities. The sum of squares are exactly the expressions we derived. So just write their abbreviations here. So we have the sum of squares regression, and then the sum of squares residual. And the reason this works out nicely is because we showed that these two add up to the sum of squares total. Okay, so remember here, both of these columns add up to the total row. Okay, and then the degrees of freedom also are related to the variances that we've already seen. Okay, so n minus 1 is the denominator for the sample variance of the responses, and n minus p minus 1 is the denominator of our estimate of the residual variance. Okay, so that's sigma squared hat divides by the residual degrees of freedom. Sample variance of y divides by the total degrees of freedom. Okay, and then we can remember that these add up, so therefore the regression part has p degrees of freedom. Okay, so we can remember this, you can think of this p as in beta 1, beta 2 up to beta p. It's the regression parameters not counting the intercept. Okay, so those are the quantities we've seen. Now, one reason the ANOVA table is useful is it allows, as we'll see in the next few classes, it will help us do various hypothesis tests concerning the significance of regression models. Okay, so I'm going to fill in the last two columns as well, and we'll talk about those later. But let's complete the table so that we have this for completeness. So we have the mean square column, and the mean square simply takes the sum of squares and divides it by the corresponding degrees of freedom. So the mean square for regression is to take sum of squares on regression and divide it by p. Okay, so this is sum of squares regression divided by p, and then likewise with residual, take sum of squares residual and divide by its corresponding degrees of freedom, n minus p minus 1. Okay, and I do want to point out that this quantity we've actually already seen before. Okay, so this guy. So the mean square residual, we've already seen. So what is this quantity? This is in fact our estimate for sigma squared. So this is sigma squared hat. Okay, so this part of the ANOVA table actually is a quantity we've already seen. It's our estimate of the residual variance. Okay, so basically the mean square. So let's just comment here. The mean square takes the corresponding sum of square and divided by its degree of freedom. Okay, so I'll abbreviate mean square by MS, and then sum of squares SS. And so the last column here is the F statistic. Okay, so I'm just stating it now. We're going to come back and look at the F distribution and F test in much more detail in the next lecture. Okay, so the F value is to take the mean square for regression and then divide it by the mean square for the residual. So it's taking this value, so mean square regression divided by mean square residual. That's the so-called F statistic. Okay, so this is considered a complete ANOVA table. So you're not obligated to. You don't need to fill in. So you don't need to fill in anything here in this box, and you don't need to fill in anything here either. Okay, so these are the key quantities. These two columns add up. Mean square are calculated from these first two columns, and then finally F statistic summarizes the ratio of the mean square. Okay, so suffice for now. Let me just make a note about this F statistic. Okay, so this is, we'll use this one later, used to test, for example, overall significance of regression. Okay, and then we're going to come back to this. We're going to see this in full detail next time. Okay, so now we have the structure of the ANOVA table. And remember the first question I posed at the beginning of the class was, well, how do we measure then how well the regression model explains the response variable? And so we get one measure of that by in terms of the quantities we see here in our ANOVA table. And so the first way to assess that is a quantity in terms of these sums of squares, and it's called R squared. Okay, so we call coefficient of determination okay, and the symbol for it is R squared with a capital R. Okay, so this guy is the coefficient of determination. Okay, and so R squared is defined as the ratio of the sum of squares regression divided by the sum of squares total. And so since we know in the decomposition that the sum of squares regression and residual add up to the total. Okay, so you put total in the denominator. This can equivalently be written as well, 1 minus the sum of squares residual over sum of squares total, because the two sum of squares add up to the total. And so we see right away that that clearly R squared is a number between 0 and 1, because it's measuring a proportion. the proportion of these sum of squares over the total. Okay, so R squared is a proportion, and so its interpretation can be written like this. So it's the proportion. Well, the proportion of what? Okay, so what did we say at the beginning? Well, the sum of squares total is one way to measure the variability in the response. Okay, so it's the proportion of, so we can say, so it's the ratio of the total variability in the response. So we can call this the proportion of variation. And specifically, we're talking about variation in our response variable. That is explained by the regression model. Okay, so as we argued, we'll show you the picture. The sum of squares regression is the difference between the overall mean of the response and the regression line. Okay, so that this is a measure of the proportion of variation that's explained by the regression model. Okay, and so in other words, the larger R squared is, so the closer R squared is to 1, the better the fitted regression line models the responses that we have in our sample. So let's just make the connection between these three things. So in a sentence, we can say the larger R squared means the fitted values are closer to the observations yi. And in turn, so if the fitted values are closer to the observations, that means the residuals are small. And that means you have a smaller sum of squares residual. Okay, so R squared measures the balance between these two components. Okay, so the larger it is, that means the remaining fraction is the. So remember, the remaining fraction is represented by the sum of squares residual over the total. Okay, so that means the residuals. You have a large R squared. That means the residuals tend to be small. In other words, the fitted values are close to the observations with the yi's. Okay, so therefore we can see how from the mathematics and the picture, and then from this. From this definition of R squared, how this is one way to measure how close the fit is to the data. Okay, and so as a side note, again, this is why I asked you to do one of these exercises on your first homework. Is why now we can see why do we call this R squared? Well, as you were asked to show in your first assignment, R squared has a very nice interpretation, especially in the case of simple linear regression. So let's just make that note here. In the simple linear regression case, R squared is simply the square is equivalent to the square of the correlation between the x and y's in your sample. Okay, so note that. Okay, so see here again from your first homework. In the simple linear regression case, r squared is simply equivalent to the square of the sample correlation between x and y based on the sample. Okay, so x1, y1 up to xn, yn. Okay, so usually we denote. So when we introduced sample correlation, okay, so this which we denoted this by the sample correlation by lowercase r. Okay, so this is to cap r squared is the generalization to that. Of course, it's not a measure of a sample correlation between two variables in the multiple linear regression case, but you can see that it has a similar, it has a parallel sort of interpretation. Okay, so again, we can illustrate that very cleanly for a simple linear regression. So here's another visual. So simple linear regression is nice because I can draw pictures to illustrate these points. Okay, so let's draw a couple pictures. Let's draw a picture for r squared equals 1, and then let's draw another picture for r squared equals 0. So we can illustrate this point. Okay, so let's start with r squared equals 1. So if r squared equals 1, in fact, again, this is something I asked you to think about already on your homework. So let's draw a picture now. Okay, so here are some. Yeah, let's draw a regression line first. Okay, so clearly x and y are correlated. And in fact, if r squared equals 1, that means the sum of squares regression is equal to the sum of squares total. So in fact, the sum of squares residual, that means is 0. So in other words, all the residuals are 0. So therefore, the sum of squares, their sum of squares is 0. So as a picture, it means all the points lie perfectly on the regression line. The regression line goes through all of the points. Okay, so this is r squared equals 1. So that means the residuals are 0, and in fact, the fitted values mu I hat are equal to the observations. Okay, so this is the extreme case where the regression line perfectly fits our data. On the other hand, well, what does it look like then? Now let's imagine, well, what if r squared was 0? Okay, so let's also consider this case together. So if r squared is 0, that means the sum of squares, now the sum of squares regression is 0. Okay, so if sum of squares regression is 0, well, what is the fitted value? Well, the fitted value. Okay, so according to the sum of squares decomposition, what is the model then predicting for yi? Well, it's simply predicting the sample average y bar. Okay, so in the simple linear regression case, what does that mean? Well, for the estimate, so that means y is not related to x at all. Okay, so in other words, beta is 0, so that means our intercept estimate is y bar, and then our slope estimate is 0. Okay, so what is that going to look like in terms of a picture? Well, our regression line is simply the horizontal line. So this comes back to the first picture I drew, where I said, well, if you don't do any regression, then you would. And if you don't fit a slope, so you set the slope to 0, then the equation of a regression line is simply the horizontal line y bar. Okay, so let's draw y bar. Okay, so it's the line with slope 0. And so that is, if that is that's the equation line of best fit. In this case, that means there's no linear relationship between x and y at all. So what does that mean about our observations? Well, let's draw some scatter plot with some example points. Well, it means our observations are simply they're just a random scatter around this line, so that when you fit the regression line, there is no linear relationship between x and y. So you just have a random scatter around this line. Okay, so that's how we would illustrate r squared equals 0. Again, it's easiest to draw the picture when we just have one predictor. So these would be what r squared equals 1 and r squared equals 0 would look like for simple linear regression. Okay, now let's illustrate this numerically now by revisiting one of the examples we did in R. So today I will show you the ANOVA table on the board and talk about it, and then we will come back to show you how to do ANOVAs in R, but we're going to talk about a few other things first. So let's do a numerical example. Okay, so I'm going to reuse the rocket data set here. Okay, so let's make this a table. So we have source. Okay, so let's write down, let's make a regression, and residual, and then total. Okay, degrees of freedom. So just to remind you, in this example, okay, so we had two predictors or explanatory variables. They were nozzle size and the propellant ratio. Okay, so there are two x's in our model, so therefore the degrees of freedom for the regression is 2. We estimated for these two predictors, we estimated beta 1 and beta 2. The other thing here is the total. So in this case, there were 12 observations. And so the total degrees of freedom is one less than n, so this is 11. And then the residual degrees of freedom we already know from when we did the estimates for this example that there were 9 degrees of freedom. And so there's so now we know there's a few ways to see why this is 9. So one is through this ANOVA table. We know that 2 plus, so this must be adding up to 11, so 2 plus 9. Alternatively, as when we did the estimates, we also remember that the residual degrees of freedom is n minus p minus 1, okay, because we estimated p parameters for the predictors and then 1 parameter for the intercept. Okay, and so I need to give you some numbers so we can do calculations. So the sum of squares. Okay, so based on the fitted model, we can calculate the sum of squares terms. So this is 846.2, and then the sum of square for residual is 63.42. Okay, and so today we learned that in general these add up to the total sum of squares. So if we add these two up, that's 909.62 as the total sum of squares. Okay, so once you have this information, we can fill in the table. So we have our mean squares. Okay, so mean square is simply the sum of squares divided by its corresponding degrees of freedom. So 846.2 divided by 2, so it's around 423.1. And then the mean square residual is sum of square residual divided by the residual degrees of freedom. So that comes out to be about 7.05. Again, I want to point out this number. 7.05. Well, what do we know about it? This is, in fact, the mean square residual is our estimate for sigma squared. So this is sigma squared hat. And in fact, if you look back at our summary R output for this example, we'll find that this is the number that at the bottom of the summary output of R's LM function. It tells us that it tells us the estimate of the residual variability. Okay, so that's how that fits in to this example. And so the last thing is we can calculate the F ratio. So that's simply the ratio of these mean squares, which in this case, we divide 423.1 by this. So after some rounding, it's about 60. Okay, and so later we'll talk about how this value can be used for the ANOVA F-test. Okay, so all right, so this is the ANOVA table, and so the last thing I want to mention is R squared. So what is R squared for this example? Okay, so what can we say about how well does this regression model explain the response, or so the response is, remember the response here is the thrust. Okay, so according to this this ANOVA table, we see that R squared is this ratio, so the sum of squares regression, so 846.2 over 909. Okay, so this is about, which is about 0.93. Okay, so that's pretty high. Okay, so from what we said, that means the regression model. So the regression model with these two predictors. So with nozzle size and the propellant ratio. Explains 93% of the variation in the response, which in this case is thrust. Okay, so that's the specific interpretation of R squared in this case. So much of the variability in the response is explained by this regression model, which has two explanatory variables. Yeah, and so generally, so you look at this ratio between these sums of squares. Gives us a good, or one metric for the fit to the fit of the regression model to our responses. And the last thing I want to point out is, well, after you divide through and get the mean square and you calculate this F statistic, you notice generally if the regression sum of squares is large relative to the residual, this number we get at the far right, this so-called F statistic, which we'll talk about more next time, it's going to be large, okay, because the ratio of these two mean squares. All right, so that's all I want to cover today. So let me pause to see if there are any for a moment to see if there are any questions about what we talked about today. Okay, so I don't see any questions. So we will pick up on this. We will talk about F-tests in Wednesday's lecture. So we'll see you on Wednesday's stream.